5,000 meters below the surface of the Pacific Ocean, where no sunlight has ever reached, and the pressure is enough to crush steel, a team of scientists sent something down that had never been tried before. Not a human, not a standard probe, an AI-powered autonomous drone built to see, think, and adapt in real time. What it came back with stopped the entire research team cold. Nobody expected what the footage showed. The mission started as a mapping operation. A joint research effort reportedly involving oceanographic institutions across 3 continents wanted to survey the Clarion-Clipperton Zone, a vast unexplored abyssal plain stretching 4.5 million square kilometers between Hawaii and Mexico. Previous expeditions had used basic landers and remote-operated vehicles tethered to ships. But those tools had limits. They could only go where the cable allowed. They could only see what a human operator thought to look at. The AI drone was different. It was trained on thousands of hours of deep-sea footage, geological surveys, and biological data. It could identify anomalies faster than any human observer. It could make decisions where to turn, where to hover, where to look twice without waiting for a signal to travel back up 5 kilometers of ocean. Scientists called it the first truly autonomous deep ocean intelligence mission. What they didn't expect was what the intelligence would find. The drone's first pass over the seafloor was routine. Rocky sediment, scattered polytalic nodules, the potato-shaped mineral formations that mining companies have been eyeing for decades because of their rich deposits of cobalt, nickel, copper, and manganese. Strange, deep-sea creatures drifting in the blackness, nothing outside of what the models predicted. Then the AI flagged something, not with an alarm, not with flashing lights. The drone simply stopped, hovered, and redirected its sensors toward a patch of seafloor about 30 meters wide. According to mission logs, it repeated this behavior 4 times in the same location before the surface team even noticed. When the researchers pulled the data, they found it, an electrical signal, faint, steady, completely unexplained. The seafloor was generating voltage. Researchers initially assumed instrument malfunction. At 5 kilometers down, equipment behaves strangely. Pressure distorts metal housings, cold affects circuitry, saltwater finds every gap. But the AI drone had redundant sensor arrays, and all of them were reporting the same thing. A low-level sustained electrical current rising from the mineral nodules on the ocean floor. Here's why that matters. Those nodules, the same rocks that mining corporations want to extract by the millions of tons, appear to be doing something that nobody had predicted. Under the extreme pressure of the deep ocean, when their metallic composition comes into contact with seawater, they generate microscopic electrical currents, and those currents are just strong enough to do something extraordinary. Split water molecules apart, oxygen and hydrogen separated, released into the surrounding water. Oxygen in total darkness, 5 kilometers down with no sunlight, no photosynthesis, no living organisms producing it. The AI drone had just helped confirm one of the most disruptive scientific discoveries of the decade, what researchers are now calling dark oxygen, a completely non-biological geochemical process that produces breathable gas in conditions previously considered incompatible with life. The implications started cascading almost immediately. Marine scientists had to reconsider their models of deep-sea ecosystems. If oxygen is being produced at the seafloor geochemically, then life down there may have access to resources that nobody accounted for. Strange creatures already live near hydrothermal vents without sunlight, surviving on chemical energy instead. But this is different. This is oxygen, the same molecule that powers nearly every complex life form on the planet's surface, quietly being manufactured in the dark. Astrobiologists took note. Europa, Jupiter's moon, has a vast ocean beneath its icy crust. No sunlight penetrates, but it has a rocky, mineral-rich seafloor. If this process happens on Earth without sunlight, could it happen there? Could it happen on Enceladus, Saturn's moon, where geysers of water erupt through the ice, suggesting a liquid ocean below? Suddenly, the search for extraterrestrial life shifted, not because of what we found in space, but because of what an AI drone found 5 kilometers under our own ocean. But the discovery didn't stop at oxygen. As the drone continued its survey, its machine learning systems flagged something else, something even harder to explain. Geometric patterns, not random sediment formations, not the irregular shapes of natural erosion, near perfect mathematical structures pressed into the seafloor, spirals, grids, tessellated ridges. The AI had been trained to distinguish natural geological formations from anomalies. It had flagged these as anomalies repeatedly. When the surface team examined the time-stamped footage frame by frame, something became clear that was almost impossible to accept. The patterns were changing slowly, imperceptibly slowly, but changing, ridges extending, spirals tightening. The seafloor was not static, it was in motion, not from tectonic activity, not from current or tide. The sensors showed none, the electromagnetic data showed something stranger. Tiny fluctuations in the local magnetic field synchronized with each shift in the pattern. Mission logs described the moment the team put it together as one of the quietest rooms any of them had ever sat in. Whatever process was producing the electrical signal, whatever geochemical mechanism was separating water molecules in the dark, it was also somehow influencing the structure of the seafloor itself. Shape, energy, synchronized. Nobody had a model for this. The AI drone had gone down looking for geographic data. It came back with evidence of a process operating on the ocean floor that science had not previously described, predicted, or prepared for. The lead researchers, speaking carefully and without overstatement, described it as a system, not a single reaction, not a one-time anomaly, but an ongoing, stable, self-sustaining process that had almost certainly been running for thousands of years undetected under 5 kilometers of ocean. And here's the part that changes everything. The polytalic nodules at the center of this process, the ones generating voltage, the ones enabling dark oxygen production, the ones now suspected of influencing the magnetic and structural behavior of the seafloor, are the exact same nodules that deep-sea mining companies have permits to begin extracting. The Clarion-Clipperton Zone is the primary target of the global deep-sea mining industry. Companies are already mobilizing equipment. Regulatory approvals are in motion. The plan is to harvest these nodules by the millions of tons to meet the demand for EV batteries and renewable energy infrastructure. Scientists working on this data are now asking one of the most urgent questions in modern oceanography. If we remove these nodules, do we shut off an oxygen-producing system we don't fully understand? Do we destroy ecosystems that may depend on it? Ecosystems we haven't even fully discovered yet? Could we be eliminating the very evidence that might teach us how life first survived on this planet, or how it might survive somewhere else in the solar system? The AI drone went down to map a seafloor. It found something that changed the map entirely. 5,000 meters below the surface, in total darkness, under pressure that would flatten anything not built to survive it, the ocean is doing something it was never supposed to be able to do, and we almost missed it entirely.